welcome to another module in this massive open online course. So we are looking at source coding, that is representing the symbols emitted by the source as a sequence of binary symbols, right, as a sequence of binary bits of information, and our aim is to maximize the average length of code, that is the average number of binary symbols or binary bits used to represent each symbol. All right. And in this context, we have looked yesterday, we looked in the previous module at different kinds of codes. We have looked at a fixed length code. We have also looked at a variable length code. Okay. So let's go about this. So let's continue our discussion on this aspect of variable length code. For instance, with m equal to 4, we have seen an example of a variable length code. S0 is 0, the alphabet S1 is represented by 1, S2 is represented by 0 0, and S3 is represented by 1 1, and we see this is a variable length code. In that different symbols have different bits. Different symbols have different number of bits. Okay, this is a variable length code. However, we have also seen that this is not uniquely decodable. This is not uniquely decodable since you have the sequence 0 0 0, this can either correspond to S0, S2, or it can correspond to S2, S0, and so on. Okay. So the not uniquely decodable, which means that the original, that is the coded symbol sequence, this implies the coded symbol sequence cannot be perfectly reconstructed or cannot be perfectly recorded. And obviously that is bad. That is, once we code the symbols, obviously we have represented them using a sequence of binary bits. We would like to or you stored them using a sequence of binary information bits. One would like to obviously at a later time or at the receiver, if they are transmitted across a channel, recover the original symbols by looking at this sequence of binary bits. Now if the sequence of symbols cannot be recovered from these binary bits, right, then there are going to be problems because the original message is lost. Alright, so it is a lossy coding and the original message cannot be recovered. So obviously we are interested, naturally we are interested in designing uniquely decodable codes, that is codes from which there is a one-to-one mapping, that is one-to-one mapping from the that is for any that is there is it's a mapping that is basically for any set of from a corresponding to any set of sequence of binary information bits, the corresponding symbols can be uniquely recovered. That is, there are no two sequences of symbols which are mapped to the same sequence of information bits. Okay. So we would like to design uniquely uniquely decodable codes. And for instance, if we can take an example again, you can see that S0, S1, S0 is 1, S1 is 0 1, S2 is 0 0 1, S3 is 0 0 0. You can see this is a uniquely decodable code. For example, if we receive the symbol, if we receive the sequence 1001, I can immediately decode this as S0 followed by S2. Okay. So, there is no other symbol sequence corresponds to this bit. So, no other symbol sequence corresponds to this bit sequence. Okay. Okay. So, this is a uniquely decodable code. Now, in part the reason for this you can see is because if you look at the set of code words, alright, you have 4 code words corresponding to the 4 symbols. You can see that no code word is a prefix of another code word. Okay. You can see from this that no code word is a prefix of no code word is a prefix of another code word. Okay. So, no code word, but however, if you look at this, you can see that S0, that is 0 is a prefix of 0 0. So, S0 or code word for S0 is a prefix of the code for prefix of code word for S2, right. Here the code word is a prefix, the code word of S0 is a prefix of the code word for S2. Okay. So, here you can see no code word in this uniquely decodable code. S0 is 1, S1 is 0 1, S2 is 0 0 1, S3 is 0 0 0. No code word is a prefix of another code word. Okay. And such a code is known simply as a, this is known simply as a prefix free code, or it is also known as a prefix code. Sometimes it is explicitly called as a prefix free code. Okay. A prefix free code. Or simply a prefix code, sometimes it is also known as a prefix code. Is basically that no code word forms a prefix of another code word. Prefix means something that is placed before, something that is in front of another word. A prefix of a word is something that is in front of another word, right. So, no code word, a code is known as a prefix free code if the mapping is such that no code word forms a prefix of another code word. Okay. Now, such a code, a prefix free code, is uniquely decodable. So, a prefix free code, the importance of a prefix free code is that a prefix free code is uniquely decodable. This is uniquely decodable. Moreover, a prefix free code is also known as an instantaneous code. Prefix free code is also known as an instantaneous . Instantaneous code implies that you don't need to wait for the next code word to decode the current. So, that is each code word is decodable by itself. That is, it is not necessary to wait for the next code. So, what happens in an instantaneous code is, for instance, if you look at each code word, correct, the moment you look at a code word, it can be mapped to a symbol. You don't need to wait to the next code word to begin. For instance, if you take a look at this, let's again take a look at this. Let's say I have 000 followed by 001. Okay, so let's say I have this code 000 followed by 001 followed by let's say 1. Okay. Now, the moment you look at 000, I can map it back to S3, correct. The moment you see 001, I can map it to S2. The moment you see 1, I can map it to, I don't need to know, no need to find, I don't need to know where the, no need to wait until, not, it is not necessary to wait until the next code word. This is known as, such a code is known as an instantaneous code. Okay, such a code is known as an instantaneous code, and the prefix free code and an instantaneous code can be shown to be one and the same. That is, a code is an instantaneous code if it is a prefix free code, a code is a prefix free code if it is an instantaneous code. Okay, so a prefix free code and an instantaneous code, and therefore they are uniquely decodable. Prefix free code and instantaneous code. And instantaneous code. And both of these are uniquely, or both of these are uniquely decodable. That is, given a set of coded bits, I can map it to a unique set of information, I can map it to a unique set of symbols. Okay. So, prefix free codes and instantaneous codes, and we are interested in designing such codes, that is basically instantaneous codes or prefix free codes. So, we will focus, and of course, one important point to note here is that uniquely decodable does not imply, that is, in other words, there can be other codes other than prefix free codes which can also be uniquely decodable, but we will not be looking at them. Alright. One of the most important class of uniquely decodable codes, or one of the most convenient, let us say frequently used or convenient class of codes which are uniquely decodable, are basically prefix free or instantaneous codes, and we will be interested in the design of such codes, that is, how to design the prefix free, design a prefix free or a uniquely decodable code for a source with a given set of symbols with a set of probabilities. That is, we are looking at a discrete, as we have clarified in the previous module, we are interested in looking at discrete memoryless sources with a set of symbols with a fixed set of probabilities, and the probability of each symbol does not depend on the probabilities of the symbols generated in the past. There is a probabilities of symbol at time instant k do not depend on the probabilities on the symbols generated in the past. Okay. And of course, let us now look at the average code length. That is, this is an important metric because this is basically going to decide the efficiency of code design. So, what is the average code length? Now, the average code length and its relevance to compression. Now, the average code length, for instance, let symbol SI be represented using Li bits. Example, S1 is represented in 000 equal to 3 bits, that is length equals to, so L1, the length of S1 equals 3 bits. Okay. Now, let the probability of occurrence that is probability x equal to SI, this be equal to Pi. Now, the average code length or average code word length is defined as summation over all code words I equal to 0 to m minus 1 Pi Li. So, average code length L bar, let us denote that by L bar, the average code length is summation I equal to 0 to m minus 1, that is the average, that is you have the length Li weighted by the probability Pi. This is the average length of the code, average length of the code. Okay. Average length of the code. And what we would like to do now is basically we would like to develop efficient codes which minimize this average code length, that is average number of bits that is used to that is required to represent any symbol generated by the source. So, an efficient code is one which has the obviously which has the least average code length, because that requires the lowest number of bits on average to represent the symbols of the source, and naturally it is therefore makes it easier to communicate, to transmit information over the channel. It makes it easier to store the symbols generated by the source by coding them appropriately, because the space that is going to be occupied by the bits, the coded bits, is going to be minimum for this efficient code. So, what we are interested in is we would like to minimize average length you would like to minimize average length and as well as develop fundamental insights into the code design process. That is, for instance, we would like to ask the question, for a certain source which generates certain set of symbols with certain probabilities, what is the lowest average code length that is possible? That is, how low can I get the average code length to be? All right. That is a fundamental, and therefore one can, using the answer to this fundamental question, one can target an appropriate code length. All right. So we are not only looking at designing efficient codes, but we are also interested in characterizing how efficient can that process be, how low can the average length, code length be for a source with a given set of symbols with a set of probabilities. Okay. So we would also like to ask the question, we would also like to generate some fundamental insights into this code design process. Okay. So in the sense, how low or basically what is the minimum, let us put it this way, what is the minimum possible average code length for a given source. What is the minimum possible average code length for a given source. Okay. So this is basically what we would like to. Alright, so basically in this module we have completed our discussion regarding the codes. What we have seen is, we have seen uniquely decodable codes and an important class of codes known as prefix free codes, or which are basically where no code word is a prefix of another code word, or which are also known as instantaneous codes, because one need not wait till the next code word to decode the current code word. Alright, and what we have said is, we are interested in designing such prefix free or instantaneous codes, and also we are interested in answering some fundamental questions as how low, alright, what is the fundamental bound on the average code length for any code that can be designed for a particular discrete memoryless source. Alright, so that will help us design. So we would like to come up with efficient schemes to design codes, and we would also like to characterize their efficiency. That is, how far are we from the lowest possible average code length that can be achieved for a particular source with a certain set of symbols given a certain set of probabilities for the symbols. Alright. So with this we will stop this module here and look at other aspects in the subsequent modules. Thank you very much.